Okay, so let's get started. And so we have an hour to go, and we are going to rush through a lot of material. Okay, so this material is rushable, so I can go at that speed because we know the basics. We know what we are going to look for. Okay, so the primary thing we know is we can build linear models. We know how to do gradient descent on linear models. We know how to regularize them and derive solutions with some desirable properties. We also know that if we build simple models, classifiers become linear. Posterior probabilities are sigmoidal. They're very limited. So we have to go and build nonlinear models. And that's what the whole of machine learning is now about. Yeah. How do you build nonlinear models that do not restrict to a simple linear class boundary, but can form combinations of these little pieces and form more complex class boundaries. So if the data distributions are more complex, multimodal, and so on, then you can form nice class boundaries and learn better than simple models. The balance to strike is that with the simple linear case, learning becomes easy. We had a closed form solution in terms of a zero inverse. Yeah, so it's very easy. When you go to complex models, the error functions are no longer quadratic. The error functions will have local minima. And the best you can do is to reach by gradient descent a local minimum close to your starting point. Okay, and that's the only tool we have. But there are other solutions as well, which needs to be mentioned. In between, I'm going to talk about a thing called radial basis functions. What we might do is in your data space, your data may be complex. You want to build a nonlinear model to model this data, either to classify or to do regression. But what you could do is to transform the data by a fixed nonlinear function or fixed set of nonlinear functions, and then do linear learning on that space. Okay. A classic example of this is signal processing and Fourier transforms. So we have complex signals like music or speech, and these complex signals consist of some fundamental frequency, like in my speech, the frequency at which my glottis is vibrating, yeah, and harmonics on them that are induced by the shape I hold my mouth in. Yeah. So if you took the complex signal in time, it may look complex. Well, complex not in terms of complex numbers, it may look funny and complicated. But if I decompose that by Fourier transforms, then I will have a certain weight for the fundamental frequency, a certain weight for the second harmonic, a certain for the third harmonic, and so on. Yeah. So I can make a transformation that is nonlinear and fixed. And if that fixed transformation I can choose in some sensible way, yeah, then on top of that, I can apply a linear model, which could be the perceptron or the linear regression, and solve my problem. And sometimes I cannot find sensible fixed nonlinear transforms. I've put in a full-blown nonlinear model and train it by gradient descent and variance of it. Okay, so that's what this topic of radial basis functions is. There is a lab on this which you can work through. So I'll just very quickly rush through that and then go to multilayer perceptrons from there. Yeah. What do? We fix a nonlinear part in a data-dependent way. Yeah. Fourier transforms is not data-dependent. It has a frequency and harmonics, sinusoids. Yeah. But we can find a nonlinear transform, and then we can write a model of this form. So here's the model. The model says some function that I want to have, which is my regression, this is going to give me my targets, is going to be obtained by a weighted sum of m basis functions. Okay. And each of these basis functions is weighted by lambda. So each of these, so j going from 1 to m, so you have lambda 1 up to lambda m. And the shape of the basis function is some nonlinear function. Sometimes we often like to put Gaussians in there. Yeah, some nonlinear function of distance from the data to some point in that space with a scalar. Yeah, are you with me when I read this? Yeah, so this is a nonlinear function, but it's a fixed one. And that fixed one has several points in the space as locations, if you like, a scaling factor, which tells you about the scale in which these measurements are being taken, maybe. Yeah? And a weighted sum of these is going to give me G. Okay. So if I can fix sigma an MJ in some ad hoc way. I might do this by clustering data. So say I have lots of data distributed all over this place, and the data is very concentrated in this part on the piano and not a lot in the back there. Then by cluster analysis, I might discover this point and the piano point. Then I can put M1 and M2 over there. Yeah, I can get a sense of scale by how far these corners are. Yeah, and I have an idea of sigma. So I have two basis functions, one located here, one located here. And the exam grade you will get in your machine learning course is going to be given by an equation like this. Yeah, this will have piano location, this will have my location, some scale parameter, and a Gaussian sitting on it fixed. Yeah, then you can regress on the exam grade to compute only lambda1 and lambda2. Yeah, and that's a linear problem. It then becomes a linear problem. Once I have fixed by some rule the nonlinear part, then estimating this becomes a linear problem, because it just says weighted sum of this and that gives me gx. That's a linear function. Yeah, so it's linear in the parameters, but some sensible, common sense, ad hoc, intuitive way of fixing this. Yeah, so if I did that, what am I doing here? I'm trying to kind of think that there is something common between people who are sitting in this part of the world in terms of machine learning and people sitting on that part of the world doing machine learning, right? So if these guys are very, very good in machine learning, those guys are not, then the function here will, function located here will achieve a higher weight in predicting the grades of high-performing machine learners, and that will be suppressed. Yeah, so that's the interpolation. It's a two-dimensional interpolation sitting here, modeling the exam grades with one part fixed and the linear part learnable. Yeah. So we can think of centers. And so I'm just going to flash through the notes, and you can go through that at your own time, and you can think of this. I mean, the idea radial in this context comes from this one. And we also can have polynomials here. We can have various things here, but RBF is a little bit common because if you go and handle any problem with support vector machines, kernel machines type methods, the most common ones that are used as nonlinear transforms are based around radial basis functions. And the reason these are appealing is because of this local property. So I might say something in the vicinity of the piano and something in the vicinity of this lectern here have some information bearing with respect to the distribution that's out there. Okay, so if I can discover these by, say, cluster analysis, for example, and then your exam grade prediction becomes a linear problem. Okay, so how do we solve this? Maybe I should get very quickly to where this is solved. It will be similar to linear regression. Where is that matrix that I have? So these basis functions could take linear Gaussian multi-quadratic. That's the literature is full of this sort of thing. That's the important part. So what I'm going to do is you gave me n data, yeah, with inputs as x1, x2 up to xn. And you asked me to model this by a radial basis functions model, which has capital M basis functions. Yeah. And you gave me targets f1 to fn. Yeah. So the x1 to xn and f1 to fn are precisely the way you set up the linear regression problem for me. You gave me x1, x2, xn, and targets f1, f2 up to fn, and said fit a linear function between those two, and we learned how to do it in the morning. Here, I'm going to fit a nonlinear relationship between the x's and the f's, and the way I'm going to do this is by projecting or transforming each of the data through these m basis functions. So look at the first line. I'm taking data x1 and chucking it through the first basis function. Yeah, the first basis function is phi of x1 take away m1 scaled by sigma. The second basis function is phi of that same data. How far is it from m2 scaled by sigma? And then through m basis functions. So what I have done in the first row is to take a p-dimensional x vector that you gave me and put it into an m-dimensional vector in the first row. Is that kind of clear? So when you solve the linear regression, what I did was I constructed a matrix called Y. I took each of the data that you gave me, made it horizontal, yeah, and put it as rows. So rows of my Y were the data that you gave me, input data. The target was F, yeah, and so I have the same F here. Now what I'm going to do is I'm going to take each of this data and transform that data from an initial p-dimensional space to an m-dimensional space by taking it through each of the basis functions. Okay, so you can imagine, so your initial data was, say, in 2 dimensions. So every point over here, and then suppose I have 3 basis functions. I'm going from a 2-dimensional space to a 3-dimensional space in which each data is going to live. And that transformation from 2 to 3 is nonlinear. And that nonlinearity is fixed. Yeah, I'm going to fix that based on some understanding of the problem, some judicious things I can do. I might even say something ad hoc, right? But I have done that transformation. So in that nonlinear space, I'm now going to solve simply a linear regression problem. Yeah, so I would define an error. That error would be y times lambda, which is what my model is going to predict. Take away the target, square it, and I think there should be a summation. Might have no, this is matrix, so there's no summation. Yeah, and minimize it with respect to lambda, and you would have for lambda exactly the same pseudo-inverse solution that I had before. Yeah, so just the same way with the linear model, I write the error as this norm and minimize it with respect to the weights, which were A in the morning. Yeah. Now I have transformed all the data into a different space, and in that space, I just solved this one. Yeah. So the problem then is, how did I set about nj and sigma? Yeah, and I would do that normally by cluster analysis or some other ad hoc rule that I have. Okay, so that will give me a way of inducing and capturing nonlinearity without falling into all the traps that nonlinear models have in terms of local minima and such. Yeah, so fixed transformation, and if that fixed transformation is a decent one that's based on some understanding of what that data is, then I can get to some good results. Okay. We can go past this, and there is a lab on this that I don't know if it's called lab 5 or not, but you will be able to implement your own RBF. You will be able to work in a regression problem of your choice. And then that's an important point in the second bullet point there. So one of the things I get my students to do is to get their own data from some repository. So UCI has a repository of machine learning benchmark data sets that are reasonably small and quite varied. And I tell the class, find a problem from there, and then you can run your algorithm on that. And maybe if somebody has published results on that data set and they have cited it, you could even compare your results against those published results. Yeah. But of course, things go wrong when you teach a class. If you set it like that and say, pick your own problem, and then when you mark your coursework, you will find almost everyone has picked Fisher's iris data set problem, which is quite a boring problem. Okay, it has historic value because it was done by Fisher in the 1930s, so you have some appeal to using that iris data set, but it's quite boring. And then you'll discover why this is so, and this is not because everybody is copying off each other. It is because the scikit-learn's demo program uses this data set, right? So yeah, so it's very easy to download. So the next version of the coursework will say Fisher is not allowed here. Okay, so that's fixed nonlinear transform followed by linear models. And then now we have completely nonlinear models where all the parts are going to be learned. Yeah, so and that's the multi-layer perceptron. So here is the architecture of this perceptron, a multi-layer perceptron. What does this do? It has things like the logistics that we saw earlier, quite a lot of them stuck together. Yeah, so, and if you write out what this output is going to look like, is going to be some nonlinear function here of weighted sums of everything that came from the previous layer. And each one of them that came in the previous layer is a nonlinear transform of weighted sums of what it saw from before. Yeah, so work from inside. So here is a weighted sum of inputs plus a bias term. A nonlinear function of that is what any of these hidden units would output. Okay. And then a weighted sum of those is what any of those output units would output. So that's there's an input, there's an output, there's a bunch of outputs, and there's a number of hidden units, which is the multi-layer perceptron architecture. For a long time in the literature, we thought a single perceptron is not good enough, therefore we need multiple layers. So we built an architecture like this. And when people had an architecture like this, the way to train these parameters, people thought this had good properties, this is a good one, but they didn't know how to calculate gradients. Yeah. So when they didn't know how to calculate gradients, the field was blocked for about 20 years or so. And then someone decided they would look up some calculus book and figure out the chain rule. The chain rule tells you that if you have an error here, then because that's a function running straight through, you can differentiate that error not just with respect to the weights that are immediately connected to this, but the ones here as well. Yeah. So what we do, we write out an error, just like we did in linear regression. We write out derivatives of that error with respect to parameters here and parameters here by applying the chain rule. And then in applying that chain rule, there is a nice little structure. Then that structure is known as the backprop algorithm, backpropagation. All it does is that just the same way you forward pass to get the output from the input, there is a term in the derivative you can backward pass to calculate derivatives with respect to these weights of the error that you define in the output. It's a nice little structure, but I'm not going to just skip past that in the interest of time, but you can look it up very easily. It's a nice, neat little structure, okay? So there was a property of circuit like this, of a transformation like this, where one could prove that if the relationship between the input and the output has some very mild smoothness properties, then that function that you need, any function that you need between the input and the output, could be approximated to arbitrary accuracy as long as this hidden unit had large enough number of them. Yeah. So you find some input, a bunch of inputs that could be where you are seated, and some target, which could be a machine learning grade, and say that's some arbitrarily complex relationship. Can you approximate this? Yeah, I can approximate this as long as this I have enough hidden units, and the function has the relationship between where you're seated and the time you spent in the bar and your machine learning grade is reasonably smooth. Again, the smoothness properties required were quite mild. That was Seibenko's results on what's known as a universal approximation property. Yeah, that took a lot of notice. People spent a lot of time on this, but it also is not exactly what we want. What we want is not to approximate a function, but to generalize to unseen data in machine learning. That's important. Okay. So the approximation property that any function could be approximated is just like saying that you give me any 3 points on a plane, I can connect them by a straight line. Yeah, can I? I can do that if you give me a sufficiently thick pen. Yeah, so that's exactly what this says. Yeah, even though it took a lot of energy, that's not a particularly useful property. But we stuck for another 20 years in the development of machine learning with a single hidden unit models, partly because when you try to compute gradients of the output error with respect to weights here, you have multiplications, you have products going from what you compute here to this one. And in between are nonlinearities that are sigmoidal. Yeah? So if you have sigmoidal nonlinearities, they can, when the weights go up, they become saturated. The gradients with respect to those sigmoids at extremes would be very close to zero. Yeah. So if we build networks with more and more layers, yeah, then as you go deeper to compute gradients, you will continue to multiply a lot by very small numbers. And when you multiply by small numbers, you very rapidly get very, very small numbers, and you get into numerical underflow type problems. So if you build networks of much deeper layers, so for about 20 years, we thought that that's not worth it because gradients propagating down would be so small that these early layers down here are not going to learn anything. Yeah. So that was known as a vanishing gradient problem, obviously, for obvious reasons, right? So people didn't bother to build deeper networks. They stuck with this one. And what did they do with this? They will pretend each unit is a logistic. So I mean, these are not particularly useful for us. So I'm going to just like, oh, this could be interesting. So remember we talked about exclusive OR? Yeah, that people thought this perceptron, that is a linear class boundary, is so silly, it cannot solve this problem. So here's a simple problem. The red belongs to one class and the black dots belong to another class in 2 dimensions. Yeah. So I won't be able to solve this problem by a single unit that we talked about with logistic. But then we could do this with is it kind of no. We could do this by this circuit. So we have 2 inputs coming here. Yeah, each one constructs a boundary. One constructs this boundary, the other one constructs this boundary, and their responses are going to be like this one for this one on the left, and that one for the one on the right. And then if I cleverly combine these 2 in the next layer, I construct that one. Yeah. So the posterior probability you saw from the logistic is a little bit like this one. Yeah, one boundary, low posterior probability, then high. Yeah. The other one can learn this one, then you combine the 2, you get this one. Can do a little bit more. Here's a more complicated circuit. The first one construct this one. It's a single logistic unit. Second one, third one, fourth one. Yeah, put them all together, you construct that one. Yeah, so that is capturing just one little region in that space, but you can do that with these 4 put together in a multi-layer single hidden unit circuit. Yeah. So that's what gives you the flexibility. So if your data is not linearly separable, it doesn't satisfy all the assumptions of the morning that are on this board, then you can put things together and build more sophisticated class boundaries, posterior probabilities, or mappings between inputs and outputs. Okay. And then there are properties of these error functions that you construct if you had these multi-layer units. They can be weird, so we won't look at the details of this. And I mentioned it this morning. In some parts of the space, the error function can make very sharp descents. In other parts of the space, the error function could be flat and boring. Yeah. So if you try to do gradient descent, things like curvature information might help you. In flat regions, you can take larger steps. In sharp valleys, you take small steps. Yeah. And there are lots and lots of saddle points in these places, which make such learning a little bit difficult. And there's quite a lot of analysis on this sort of thing. I'm going backwards, am I? Yeah, so there are many little points about this that we could just skip past. And I think there's no point in deriving the error propagation algorithm here, but just quickly run through that would be, yeah, so the idea in this, if you go and look this up, is what you will find is that there is an output at which I can define an error, and I can differentiate it with respect to the weights that link to that output immediately. Yeah, so I differentiate the error, 2 comes in front, the term stays there, then go inside, differentiate, as we did exactly with the linear model. Yeah, this is doable. But when you come to the next layer, there isn't an immediate target connected to this. Yeah, so you've got to find how to apply the chain rule in a clever way in order to compute derivatives with respect to the hidden units or the weights linking to the hidden units of the output target. Okay, so that's what the error propagation algorithm does. And there is a term that comes in there, which is the derivative of the objective with respect to the net input going into a unit. Yeah, so you have a unit sitting here. The total energy, if you like, or signal going into that unit is a weighted sum of the inputs. Yeah, so the trick in this, if you follow this literature, is to treat the derivative of the output far away with respect to the net input going into a unit. And that term can be back propagated just the same way the signal is forward propagated. That is the beautiful trick that comes about. Okay. So let's skip past that. And if you can do that, what you get? Once you do that, you get the gradient. And once you have the gradient, you do gradient descent training and keep going. So again, skip past all that. I should have deleted this before I came to the room, right? Now comes some more interesting things. Once you compute the gradient, like exactly what we did with the linear model, we can update weights. You start from a random guess, and then you keep updating little by little, and you keep going. Yeah. You can do better if you measure curvature information. Yeah. If you measure curvature information, then you can go and ask the question, can I update by a formula like this one? What would this formula look like? Your guess of all the weights at iteration m is updated by the inverse of the Hessian multiplying the gradient you compute at that point. Yeah. The gradient you compute at that point tells you in which direction the minimum is going to be. The curvature tells you how fast you might want to get in that move in that direction. But then, as we observed in the morning, this is not a very nice thing to do because the Hessian has to be inverted. Inverting a matrix is cubic in complexity, so we don't like to do that. And also, it may actually be singular and not invert if the weights or parameters going into this are correlated in some way. Yeah, then the matrix is singular, you can't invert this. So what you then want to do are various tricks around this by which you can operate in between the two extremes. By one extreme, I refer to the vanilla gradient descent with some randomly or arbitrarily in ad hoc way fixed learning rate. And the second order method, that's Newton's method, that uses the inverse of the Hessian matrix. In between these two extremes, there's a whole bunch of algorithms that enable you to do efficient gradient descent. Yeah, and I can just throw a few of them at you. One is this momentum term. What this does is you take so by delta, I'm going to say how much change I'm going to make to the weights as given by my gradient descent algorithm. Okay. So if I were to remember the change that I had at iteration m-1, then I have made a small step. I know the change that I want to make at m. Yeah, I make a convex combination of these two as what I would add to the current weight to get the next weight. You with me? So m is the current weight, my current iteration. I want to go to the next step by gradient descent. What I would normally have done is to compute the gradient where I am, multiply it by a small constant, and add it on to get this one, or subtract to get this one. What I'm now going to do is to compute the change I'm proposing at iteration m based on the gradient. Remember what I was doing in the last one, and use a combination of these to go that update. Yeah, and hence, because I'm remembering what I was doing one step before, I'm going to refer to this as momentum. And the effect this would have would be somehow to smooth that error function. Yeah, so the error function can have rugged shapes, and by computing gradients at two steps and averaging them, taking a convex combination, you're somehow smoothing it. And there's a whole bunch of tricks like this. There's a thing called quick prop someone came up with some time ago that would look at approximating the local curvature by measuring the gradient in two different places. Yeah, so we don't want to compute the Hessian as a whole and try to invert it. You look at the gradient in two different places. That gives you an idea how curved that space is. And from that, you define an update weight. Yeah. We can do line searches. So remember, when I'm talking about, it's easy to talk about one dimension, but we are actually in multiple dimensions. So what you could do is to first find a direction to go, which is the gradient, and just do a line search to see where the minimum is in that direction. Yeah. And once you have found the minimum there, sit in there and ask the question, what is the next best direction to go? And then do a line search along that. Yeah. And that's the method of conjugate gradients. The numerical algebra literature is, numerical optimization literature is full of many such tricks. Yeah. So we'll just skip past all of them. Yeah, let's conjugate gradients. And this is an important point about, so that's about training. That's about finding a minimum. Yeah. But remember I said finding a minimum on the training set that we have is not our goal. Our goal is to be able to make predictions on unseen data. Yeah. So if you have a very powerful model, then you run the risk that this powerful model will fit all your training data perfectly. So you don't want to do that. And there's a whole bunch of tricks to deal with that. We'll look at some of them here, and we'll look at some of them in the context of deep learning. What do? You can get hold of a validation set that you give me a bunch of data. When I want to train it, I want to keep a small part as a validation set. Yeah, and I would use that validation test set to check whether I'm over learning, whether I'm fitting the data too much. So as I train by gradient descent, the error on the training set will go down monotonically. The error on a holdout validation set might go down and then go up again. Yeah, so I might say I'm going to stop training over here and then quote performance on a third set that I have never seen before, so that I can claim that is what my performance of my model is. Yeah. There is another important property, and Bishop's book explains this quite well, so I want to refer you to that. And that is, if you set up a neural net with targets set in terms of this class, that class, the other class, and so on, and minimize objective function, yeah, by gradient descent training, then what it does is to approximate the posterior probabilities under some condition. So remember, we looked at posterior probabilities in the context of Bayesian classification, yeah, where we said compute a likelihood on this class, a likelihood on this class, use your prior about these classes, compute Bayes rule to give you the posterior. Yeah, this we did before. Yeah, you can take data from these distributions and train a neural net with mean squared error cost function, and what the result it produces would be estimates of posterior probabilities. Okay, so that's a very classic and useful result, and I think I'll refer you to Bishop's book to go into that in detail. Okay, so that's about what we saw in the morning about a linear model, a nonlinear model like a multilayer perceptron at this end, and in between something like radial basis functions where you can have a fixed transformation followed by a linear estimator. So those are kind of three different tools that are available to you when you go and work with regression and classification problems. What I would like to do now is to go into more recent things that are around. And this is now going to be a random walk through various topics that happen when you go from a simple shallow neural net of a single hidden layer to much deeper architectures, which is what's most fashion of the day. Okay, and that is, I say fashion because I have a fundamental conflict in my day job between myself and my PhD students. Faced with a new problem that I bring to the room, I always want to start with the smallest possible model I can think of. And if this is not good, I want to go bigger and bigger and bigger. Almost all my PhD students would start with the largest possible model that would fit into the computer. And then now the computer breaks, it's smoking, so then come down to smaller and smaller. Yeah. And then an equilibrium is reached between halfway, where they become my friends. Okay, so we just talked about universal approximation. So Cybenko's results, if you look up these names in the 80s, you will find people talking about approximation properties of models. And we stuck with using approximations of data plus regularization as a way of offering performance on unseen data. Okay. And we just talked about vanishing gradients. People knew that deeper networks are interesting, but they could not really train them well because gradients get multiplied and so on. And we have tricks to deal with it now. A lot of the thinking now is based on the observation. If you train very deep architectures, so multi-layer perceptrons with many, many hidden layers, and if you successfully train it, the kind of representations that it learns, it picks up from the data, are immensely valuable. So if you're looking at image classification problems, you think of images of trees, images of lampposts, images of bicycles. Through a very deep architecture, you can map those images from a space where they're like 200 by 200 pixels to something like a 1024 dimensional space. In that 1024 dimensional space, all these trees go to one corner, all the bicycles go to another corner, and all the lampposts go to another corner. Yeah, the representation that's being learned at that end is quite useful for the task to classify. And then you can go and probe what these representations might be, what might they be sensitive to, and so on. Yeah. So the whole nature of the beast in terms of the field now is to think more about representations. So the very popular conference in the subject is called ICLR, International Conference on Learning Representations. So we have moved beyond trying to say what we want is to learn a mapping between input and output to focusing more on what the representations that they learn are. And quite a lot of the drivers of quite a strong driver of the field now is focusing on that. Yeah, and there will be impacts of that in the way we think about it. So we could say, okay, take a chemistry molecule and what is a good representation of that? Take words in language and what's a good representation of that, and so on. That's the driver. There were also three other key developments of recent times. Recent is now already about 10 years old. One is the operation of convolutions. So convolutions are little mathematical operations on data, filtering operations on data. They're very effectively usable to extract some invariant features from images, from biological sequences, from chemical molecules, and so on. Yeah. So that's one dominant trend. Huge amounts of effort gone into GPU hardware so that you can train very large models. And another key important development, automatic differentiation. So this is something very important you can figure out, you can read about. So when I did the back propagation, when I showed you the small multi-layer perceptron, I wrote a lot of equations and said there is some neat structure. And if you go and code up that neat structure, you can compute gradients. Now we don't sit down and write these things. We compute different differentials or derivatives automatically. Yeah, and again, systematic application of the chain rule does this. And what you do, as you forward compute, you have some data going in, multiply nonlinearity, and so on. You remember what is needed to compute the total gradient when you come back using the chain rule. Yeah, and this is all coded up and sitting inside packages, which drives the field in a very beautiful way. Yeah, so if you think of differentiation, you should consciously think of three things. One is you can differentiate by with a paper and pencil, sometimes smallish problems. Yeah. The other is you can do it numerically. Yeah, you can say I evaluate something happening here, I evaluate something happening here, I take the difference, divide by how much I have moved, that gives you an idea of the gradient. Yeah, this is not that. Automatic differentiation is not that. Automatic difference, and then the third one you can think of is symbolic differentiation. So you can program a computer to recognize there's a sin x there, there is a log there, there is a plus there, yeah, and write a whole bunch of rules that will pass that expression that you have and differentiate it symbolically. Yeah, automatic differentiation is not even that. Yeah, it is computing a forward computational graph, and as you compute, you remember what are the things that's needed to apply the chain rule to compute the differential backwards. Again, that's quite a cool trick, but that's what drives the field. The other thing to note is that we started throughout the 4 hours I've been talking to you, I had a multidimensional space in which I wrote vector x, and vector x was my life. And I multiplied this by matrices and so on. Yeah. Data is not always in that form. Yeah. So data comes in many different forms. There is natural language, you can have text and sentences and documents, is data. Yeah. You can have data in the form of biological sequences. You can have data in the form of molecular structures or strings and graphs. Yeah. So there's quite a lot of interest in dealing with this sort of data. And for a long time, there were little tricks in using this data. For example, if you ask me to model text, yeah. So I can't compute Mahalanobis distance on text. Yeah, but I know how to do Mahalanobis distance. I can build classifiers using that. Yeah. So what do I do with text? What I can say, for example, is to say, let's just see in this textual documents, there are different lengths. If I can look at the vocabulary from which this text is derived, yeah, and count how many words, how many times a word occurs, then I can build a vector space which is of the same dimensions as the size of my vocabulary, and I can say which words occurred how many times. Yeah, so if my vocabulary is like 10,000 words, say, yeah, English is my third language, so it's only 10,000. You give me a document, I count how many times this word occurred, how many times this word occurred, and so on, chuck them in, I have a very sparse, high-dimensional, 10,000 dimensional vector representing any document. So there's a bag of words representation. Yeah, and then I can do Mahalanobis distance or Euclidean distance or dot product with that one. Yeah, so that has occupied text applications quite a lot. We have learned to think very differently now. So with text bag of words, or with chemistry, we have talked about fingerprints of features. I'm still on the then world. Yeah, bags of trigrams of amino acid frequencies for proteins and so on. Or features derived from known properties of those chemicals. You learned about RD kit yesterday. Yeah, so you know that. The way to think about these things now is to ask, can we learn representations of words in a continuous space? So I'm going to now think of my 10,000 words in my dictionary. And these words do not occur in language in some random way. They're heavily regulated by the grammar of the language and the semantics of what I'm allowed to say. Yeah, so these words do not live in isolation. Yeah, so marking them out in a big 10,000 dimensional vector is not particularly exciting. So can I think of a 100-dimensional vector in which these words occupy some interesting space? Yeah, and if I map those words into a 100-dimensional space, then every word is going to be represented by a 100-dimensional vector. But what's the mapping between the word and where it finds itself in that 100-dimensional space is going to be determined by data. What is the context in which these words occur? Who are its neighbors? What's the semantics of these words? Yeah, and thinking along those lines led to what's known as self-supervised learning. So we talked about supervised learning, classification clustering, classification regression problems. We talked about unsupervised learning, like dimensionality reduction and density modeling. The idea of self-supervised learning is to pull out context, pull out a representation that would capture context in which words might occur, context in which DNA combinations of DNA nucleic acids might occur, combinations in which molecules, proteins, whatever you name it, occur. Yeah, so this, I only put 4 words here. There are about 25 to 30 different kinds of data transformed to some vector space. How would I do this? So here I have just drawn this for protein sequences. So I have a sequence of amino acids forming a protein. Yeah, I'm going to represent trigrams of amino acids as my base. So my word is going to be 3 amino acids. Alphabets. Yeah, and what I would do is I would take out the middle one here, for example, and say, if you give me this one, this one, this one, and this one, can I predict what would be in the middle? Yeah, there would be 8,000 possibilities here because there are 20 amino acids. So if I took 3 at a time, I get an 8,000 dimensional space. Okay, so I'm going to throw in a very large neural network. And then I'm going to train, looking through lots of data, setting the context as input. So the light blue ones as input, and the one in the middle as the target. Okay. So what I would then end up with is a representation in the internal space of this, which will be 100 dimensions, that corresponds to what this GHI is going to be. Okay. So in a 100-dimensional space, GHI, this is a 3 amino acid thing, becomes a vector. Yeah. Similarly, any 3 amino acid combination becomes a vector because I have set up a learning problem in which context goes as input, and the thing sitting there becomes the output. Yeah. And what is a representation internally that gives me that prediction correctly? Okay. And this started with word2vec, so every word becomes a vector, and people showed some fun things with this as well, which is quite amusing. So you find the vector representation for king, you find the vector representation for man, you subtract man from king, you find the vector representation of woman, add it on, you get a result in 100-dimensional space, then go and look to see which is the closest to this 100-dimensional representation after you have done this calculation. It turns out to be queen. Okay? So somehow the underlying semantics has got captured in this representation that you can do little bits of arithmetic with words, as it were. Yeah? And that has spun off quite lots and lots of interest in various forms and shapes. So let's rush through some other deep architectures that are around and what other things do. And I need to watch time here. How are we doing? We have about 10 more minutes, is it? Sammy's not here. Okay. Well, we have 20 minutes. Sammy's not here. Okay. So convolution neural nets, what do these things do? You have a convolution operation on these inputs. There is an image that's coming in. Yeah. So if you filter this image by a small filter, yeah, by convolutions are filtering operations in signal processing, you get another image. So you throw in lots and lots of these filters and filter these, you get image. So, but if you throw 96 of these filters, you're going to have 96 images because each filter filtering an image is going to expand the data quite a lot. Yeah. Then what you do, you go and subsample it by this pooling operation. What does that do? You take an image and you take 4 or 6 or 6 by 6 square and replace it by its average. Yeah. So a large image becomes a smaller image because you have pooled neighboring pixels and sum them up. Yeah. So a series of operations where you filter by multiple filters, and filtering is a convolution operation, and then the resulting ones you subsample to reduce, is a systematic way of pulling out salient features that are sitting in images. Yeah. And there is work on people going and looking at these internally and saying that in the early times, they are likely to pull out features which are image related, like edges, like sharp textures and so on. And then when you get to the end here, you end up with something like 4096 in this particular architecture that I randomly pulled out. So an image that was 227 by 227 and RGB has now, through these series of operations, been mapped to a single vector in 4096 space. Yeah, that's the kind of thing that goes on in this world. Yeah, and to do that, you have to go through a series of convolutions, pooling, and so on, which makes it a very deep operation. Yeah. And what we can then do is you train these end to end. So you say this image goes input and a particular class, whether there's a tree or not, comes at the output. Yeah, that's all you're going to specify. And you compute gradients and you do gradient descent. This is all that's going on. Yeah. And once you do that, then again, the problem that we talked about of propagating gradients with nonlinearities can cause effects. So here's another architecture known as the residual network. What does this do? This has short circuit connections. Yeah, so along the way, you have some input X going on here, and it's subject to a weight layer and a nonlinearity and another weight layer, and out comes something. And to this, you add that input over here. The only thing you need to take care of is that the dimensionality going in here and the dimensionality coming out here should be the same. Otherwise, you can't add this, right? So that's another architecture. You build a little tool like this, and then connect many, many of these and form another deep layer. There is empirical work. There is results on which one is better. And there are 25 of these architectures in computer vision field, at least. And I think to a first approximation, I would say that the one that is latest is perhaps the quoted best, because machine learning is about monotonically improving performance, which is one of the boring aspects of it. Audio signal processing, you can do exactly the same thing, not two-dimensional convolutions, but one-dimensional convolutions. So there's this architecture became quite famous with speech modeling. So here we could talk about convolutions here, but there are also dilations here that you can think of. It's basically building models with some flexibility in there. Yeah. What do these dilations do? You're trying to convolve here based on what came immediately and what came 4 samples before that. Yeah. Over here, you're going to do a convolution based on what the sample that I saw now and what I saw in the previous point in time. Yeah, so you can build a hierarchy with spanning different regions or different temporal ranges and build a complex architecture, again, trained end to end. There's in this one, there was also a really nice step up here. What they're doing is modeling audio, yeah, music or speech, but not modeling it as a regression problem, but quantizing the sample value to 128 different levels and solving a classification problem. So you're predicting which bin this goes to, not the precise output value. But 128 different levels is good enough that you can't tell the difference. Yeah. So remember, right at the beginning, I made the comment that density modeling is difficult. Regression is easier than density modeling, and classification is the easiest because you only care about class boundary. And that's captured in this quite an elegant way, because you know that the samples being put into 128 level quantization is good enough for audio. Yeah. Maybe music, some people might hear more difference. I don't know. I'm not into that. But audio at this level is, speech at this level is perfect. Yeah, you can't tell the difference. So there are tricks like this. Then comes the idea that when you start modeling time series, the past becomes very important. So you can build an architecture, which is a recurrent neural net. So what does a recurrent neural net do? This will take a neural net with feedback in it. Yeah, so you project an output based on what you see at this point in time in the input and what you saw in the previous point in time in the hidden units. So a time delay on the hidden units chucked into the input is going to project the output. Yeah, that's the recurrent neural net architecture. So that has been around for some time, since mid-80s, mid-80s and so on. And how do you try to train them and so on? What you can think of is you can unwrap it over time. Yeah, because if you have feedback with delay, then the current thing is going to be based on what happened in the past. And what happened in the past depending on what happened before that. Yeah, so you can pretend if you unwrap this in time, then you can apply pretty much the backpropagation type ideas to compute gradients and train them. Turns out that is also not particularly strong. How far back such a model looks is difficult to control. Yeah, it doesn't look very far back. So there's this beautiful architecture called long short-term memory. It's a complicated term. What it is to construct a unit like this, which has feedback and some bit of modulation that's defined by some equations. And what this can do is to selectively learn what the important part in how long back do you want to look. Yeah. So there are these gating signals are used to control or learn to control how far back you look. Okay. So here is something we looked at with my student Manuel Nunes. What he did was to take one of these LSTM models and train it to predict financial time series, the bond markets. So after this model has learned to predict, then he goes and looks at the internal units of this to see what it does. Yeah, what is it learning? And you can then go and look to see regime switching like this. So the black, blue, red, and green are different hidden units in this model. Yeah, and the black one and the blue one seem to have learned pretty much the same thing. The red one is learning something else. Yeah, a combination of these is what's predicting the time series correctly. Okay, with me? But if you look at the green one, so in this region, the green one is going up and down like this, and the blue and the black ones go down and up like this. Yeah. If over here, the green one is dominating, and the black and the blue one has gone down. Yeah. Somehow, Manuel, having worked in the financial markets before coming to as a PhD student, thinks that the period one where this kind of switching happens, this kind of thing happens, and period two have relationships with respect to other things that are going on in the economy. Yeah. So that's, again, an important point about using machine learning, neural nets, deep learning in a modeling setting, where quite a lot of the time, the dominant part of the literature is on fitting a model, training it well, getting increased level of accuracies. Yeah, that's what you will find bulk of the papers deal with. So if I have a new model that does 2% better than somebody else's model, I'm very happy. Yeah, we stop there. But there's a lot more one could do. One could go and probe into what the model has picked up and see if that's explainable in terms of something else that's happening in the data. And at that point, you're beginning to learn something. Yeah. And in a way, that's what motivated, that line of thinking is what motivated this whole network. That's artificial intelligence for science, is about what can you pull out about the underlying thing that's going on by applying these models, not just to treat these models as black boxes that replace the human doing something. Yeah, that was a cool example. I've given the reference, you can do this. So here's a whole bunch of tricks in the remaining 2 minutes. So weight decay regularization is something we do so that we stop the model from memorizing all the training data. And what does this do? So this is similar to what we saw before. We saw a quadratic penalty. So if you have a quadratic penalty in terms of the weights, any particular value that quadratic penalty achieves is on this circle here. Yeah. Whereas the loss function that you're trying to minimize is over here. So if you don't do any regularizing, then you have the loss function here, and you will find this W star as the minimum when you go down doing gradient descent. Okay. If you constrain the weights to be by a quadratic penalty, then it's a combination of minimizing the data error and forcing this penalty is what's going to be the solution. Yeah, and the solution is going to sit here. With me? Yeah. So if the weighting, which is a gamma term I used in the morning, is very, very small, then this penalty has little effect, and you're going to find a solution over here. Yeah. If your weighting is very high, then this gamma would dominate, this term would dominate, and you're going to find a solution very close to this. Or the other way around, the inverse of that. Okay, so early stopping, I said you can look at a cross-validation, set and stop early. That has roughly the same effect as this quadratic regularize that I had. So you start from here, you go towards the minimum by gradient descent to reach there. But sometimes looking at a validation set, you have stopped, and that stopping has about the same effect as doing this. Yeah. There's another nice trick called multitask learning. This is quite cool. There is, you want to go not from X to Y, but you want to solve 2 problems at the same time, X to Y1 and X to Y2. Yeah. And if it is the case that the 2 tasks that you're trying to solve have underlying functional relationships between them, then doing them at the same time, yeah, buys you more than doing them independently. Okay. And what can you do there? You can construct a network or a model where the input goes here, and there is a hidden layer that's shared between the tasks. And then there are hidden layers that are specific to the task. Yeah. So what you're doing is you're constraining the power of the model to learn things that are common between the tasks here, some representations, and out of that comes specialism that needs that. In a way, restricting the model from exploring all the space is, again, you could see this as a way of regularizing. Yeah. Augmentation is very common as a way of restricting the model from learning. Data is often limited, but you sometimes know that there are certain types of variability that are characteristics of the data. Yeah. So with images, shift, rotate, flip, these are all very common things you would expect. So what you can do is, while you do your training, you can induce those things that you expect into the training set. So deformations like, distortion, fine distortion, there's linear transforms, adding noise, elastically stretching things. So you were only given this little 1 butterfly picture. While you train your model, you have induced all these translations and deformations into the data set, and then you train. Because this kind of variability is actually natural. It can occur. So when you go to a test data set, that test data set may be slightly deformed butterfly, but you have already learned that because you have induced that into your training set. Bagging is an extremely important thing. So in any learning scenario, if you have multiple models, Yeah, so you're trying to solve a problem. You try to solve it with different models. And if those models make uncorrelated errors, then a combination of those results is always better than any of the individual ones. Yeah, that's something fundamental. So if a model makes mistakes, you have a second model on the same problem making different mistakes. Yeah, then by combining those outputs, you can win. Yeah, so that's and that can be induced into, you give me a finite training set. I can sample from that finite training set, sometimes with replacement, sometimes without, and use those samples to train different models, and then combine those models to get better results. The idea of random forests, which you might be familiar with, is entirely based on that. With dropout is another one. This is entirely counterintuitive. What you do, you're trying to train a large model, and you propagate the data, you compute the gradient, you update. This is what we do, right? So in dropout, what you do is when you propagate and train, and every iteration, you switch off half the stuff, half the units. So you have your model with 100 units. During every pass, you only have randomly see 50 of those units. Yeah, empirically, it was observed that that produces good results. Yeah, but there is now good theoretical results showing that the effect of doing that is implicitly model averaging. Yeah, so if you train a model with randomly switching off at every pass half the units, it is equivalent to training many different models and doing model combination to do that, to achieve a result. Yeah, so that power of model combination is, or model averaging, is inherently implicitly achieved by this training trick of switching off half the units all the time, which sounds crazy, right? But it has an effect. I think maybe I should skip past autoencode. How am I on time? How long have I overrun now? Okay, so are you guys awake? Yeah. Yeah, okay. Who is not awake? I wouldn't know the answer to that, right? It's like in aircrafts, they tell you that if you can't read this, tell a flight attendant. There's a note that tells you, right? So, yes?
Just before you go on, with the regularization on the dual outputs,
yeah,
would you get a similar effect if you did a dual input? They were similar.
This one.
Yeah.
What would dual input mean?
So if you, instead of a dual output where the two outputs were similar, you gain the regularization there. If you put two inputs which were similar in the space, would you get a rise in the output if you're trying to do that?
This is slightly different, isn't it? So I'm solving two problems at the same time here. That's the way to look at this. Okay. So Y1 would be predicting solubility of something, and Y2 would be predicting whether you will kill someone or not, given a chemical here. Sure. Right? That's the problem. Okay. So because if there is a functional relationship between something that dissolves and something that kills, then I can pull out that in this space. That's the idea here. But if you're thinking of two different inputs, that's almost like saying there is an input space that has been partitioned into two. Yeah, and I don't really see a merit of doing that offline, but it's hard to say. There may be some counterexample to this, but at the moment I'm thinking from one input space, which could be some chemical molecule with which I'm trying to solve two different things. Okay, so this is another dominant thing, and I've already touched on this problem before. So you can ask to train a model by showing at output the input. Yeah, so you have, remember we had inputs as measurements in the bar in the library, and the output as exam grades of machine learning. Think of a model which has two inputs and two outputs. What goes in is time spent in the bar in the library, and output is also time spent in the bar in the library. At that point, that looks silly, doesn't make no meaning. But if you squeeze it through just one dimension, yeah, then it begins to make sense. So imagine you have a 10-dimensional space, 10-dimensional data, and you show the same data as input and the output, but in the hidden units, you only have 2 or 3 space. Yeah. So you're trying to squeeze the distribution through a bottleneck to reconstruct the same thing at the output. So the question would be, then what would it actually capture in that latent space, in that squeeze space, that is most essential to reconstruct that output? Okay, so that's the whole idea of autoencoder that has been around in the late 80s and so on. So you show this data and show exactly the same data and ask, if you were to squeeze this through this bottleneck, what's the best it can reconstruct? Yeah. If these things were linear, so if you took this data and compress it by a linear transform and then expand it out by another linear transform to reconstruct itself, then you can formally show that what the representation that you can have here is just the principal components. And that you can already imagine, because if you ask what's the mean squared error reconstruction here from a space here, yeah, then that has to be the principal components, because we talked about it in the context of data compression. We were saying that you have 2-dimensional data and you have to throw it through a single one number at a time band limited communication channel to communicate to the other guy what the data was. Then the minimum error you will make if you are sitting on the principal component. Yeah. So the autoencoder of some time ago was very quickly seen as if it were linear, it's principal components. Even if in the encoder part you have nonlinearity, as long as this is mean squared error, then this will only reconstruct, this will only find the principal components. That's demonstrable. There is a whole topic called variational autoencoder, and this is a probabilistic version of what we just saw. What you do here is, okay, so in a high dimensional space, you have data, but you have reason to believe that this data lives in a low dimensional manifold in that high dimensional space. What can you say about this? Okay, so what you want to do is to capture that probability density by having a model that can reconstruct that, starting from a low dimensional space that I'm going to call a latent space. Yeah, and in that latent space, you have a probability distribution. That probability distribution transformed by this decoder will induce that probability distribution. Yeah, that's the whole idea. I'm going to skip through the maths of this. This also, again, is a kind of headline grabbing thing. In a way, if you train up this model on loads and loads of human faces, say. So say this data is lots of human faces, but faces, if you took lots of faces in 200 by 200 pixel space, in that 200 times 200 space, faces don't sit all over the place. Yeah, faces have very regular structures, so they sit in a nice little smooth manifold. So you can capture that, you can learn that distribution. So what have you learned? There is a model that can generate the face distribution in that 200 squared space, starting from a small space in which there is a probability density. Yeah. What you can then do is to sample in this space. So you sample in this space some random point, take it through this decoder, and you will project onto some other point here. Yeah, and that point will be a face that never existed before, but will look exactly like a face. So that's cool. And that has been now being used in many other applications. Can we generate molecules? Can you generate smile strings of things? Yeah. Can you generate protein sequences? So that has caught on in many different applications. Yeah. But the basic idea is this: given a training set of data in a very high dimensional space, can I capture the distribution of that? Knowing full well that distribution would be sitting on a very complex nonlinear manifold, which is of much lower dimensions than the dimensions in which the data sits. Okay, so that's an important topic we are not covering, so we'll skip past a lot of the maths, but that tutorial is a beautifully written, well-readable tutorial. So you have pointed to that there. Something my students work on is cascade learning. So we don't like training models end to end. Yeah. So we have a lot of model. You show the input, you show the output. You train that model end to end. We think that's a little bit boring. So that's the end to end. So the way we would want to train models is in a cascade way. So what we would do, layer by layer. So we would take a model with a single hidden layer and train it. And after training it, we fix that layer. So that layer becomes a fixed nonlinear transform. In that transform space, we attach another layer and train and keep doing that. Yeah. So we thought that's a cool thing to do in 2018, already 4 years ago. A few months, and Enrique demonstrated this on some simple problems like simple image processing tasks. Subsequently, around the same time, someone had another piece of work, very, very similar architecture, training layer by layer, but they demonstrated this on a very large problem, the ImageNet challenge of millions of data. So that kind of makes sense. But there is a particular reason why I like to work with this kind of architecture where you train layer by layer. When you train layer by layer, you implicitly have a regularizer at every point because the model is restricted and cannot do too much. Yeah. So what would happen is that in early layers, the model is forced to learn coarse features of the problem domain. It cannot learn all the fine points about the data. But as you add more and more layers, then it can pick up much finer details about the problem domain. Yeah. Whereas if you train end to end, then you're leaving it to chance that what type of feature is picked up. Yeah. Why is that interesting? I'm going to skip past that. No, I'm not going to skip past that. Yeah, so this is something my favorite. I'll come back to this in a second, because now I'm stealing Sami's time. Fairly soon. Okay. So fairly soon means we should then skip past that. Given there is huge advances in computer vision, there is now a lot of interest in asking, what can you do with this in medical imaging? That's now growing as a very important field. We had a meeting with medics, clinicians, with computer scientists a few months ago. And immediately after that, a queue formed outside our offices of every medic with some imaging related problem. Why is that interesting? So look at it on the data set size. I mean, I think I can perhaps stop with this slide. Computer vision is at this end with over 1 million training images. This is driven by self-driving cars and the like. So they're very, very data rich. Medicine is not like that. There are some problems in medicine in about 100, 200,000 images. So chest X-ray type problems like this, yeah, or eyes. There are some problems that I get given which have about 10,000 data, not a lot more. There are some problems with about 100,000 data. So if you give me a problem with 100, 200,000 data, then I would start training a model from scratch, similar to what I would do here. If you give me a problem with about less than 10,000 data, I would resort to a topic called transfer learning. What I would do is train a large model on ImageNet. It's a pre-trained model. Take this model and tune it to adapt to the medical problem. Why is that feasible at all? Because images have a certain range in that space that they will live. So functional relationships or distances between images that's seen in the natural world, I can borrow into the medical world as well up to some point. Yeah, so that's workable. If you give me a problem with 100 to 1,000 images, then even that won't work because the representations that I'm pulling out in the kind of computer vision architectures that I showed are in about 500,000 dimensions. So when the number of data becomes comparable to the dimensions of the representation that I have, then I run into difficulties. So there are tricks like few-shot learning that become applicable. I also get given problems with 10 or 20 data, then I say, go away, it's not particularly interesting. So just to finish on this, on that cascade learning part that I did, there's some current work that I work with these guys. So look at this. These are chest X-ray images. And we have trained classifiers, one using end-to-end training and one using layer-wise training. And after doing that, we can go back and see which parts of the image is focusing in delivering that decision. Okay, there are tricks by which you can do that. If you do that, then when you do, let's just look at one of these, when you train layer by layer, you can induce, because you're restricting the model from learning, to localize those features that pull out the output decision. Yeah. In this data set, there is a labeling of these boxes that tell you where the medic is looking to make that diagnosis. Yeah. So these boxes are given to us. And if you train end to end, you're throwing features all over the place in order to be able to make that prediction. In training layer by layer, we can pull out very localized features that seem to match what the clinicians seem to be looking. Yeah. So I think I need to stop there. So in order to stop there, I need to go to this last slide, which says what we did not talk about. Yeah. So we did not talk about how we derived in the very last picture that I showed you, which parts of the image are telling me about that decision. That's becoming booming as an important topic because it is a bit like explaining. Yeah. So here is an image, and I'm saying this guy has a particular illness, and the doctor would want to know where is the decision coming from. And in the very early stage on the image, if you localize those features, then they might say, yes, that's where I would have looked as well. Yeah. So there's a whole bunch of tricks by which, algorithmic tricks by which you can do that kind of calculations. We did not talk about attentions and transformers. That's another very, very big topic of the day. You can ask for a particular part of the data in which you are making a prediction, but which other parts of the context is your model paying attention to? And you can formulate models that way. Yeah, that's a very big topic we did not cover. We can define information theory-based objective functions we did not cover, and there are some tricks associated with that. Graph neural nets are another big topic that's of great relevance to chemistry, proteins, and so on. We did not cover anything about modeling uncertainty. We touched on uncertainty in the context of Bayesian decision theory, but there's a whole bunch of tricks and a whole bunch of approximate inference tricks that go with this. And we did not talk about time series decision processes and so on. So